Yeah, well, we got just about everybody. So let me go back to the notes and see where we left off. I think we left off talking about macro and micro realms. And so let me just share my screen so we can keep pushing with that. And turn off my video. Yeah, I gotta switch computers. This is bad. So if the meeting ever times out or kicks you out, just log back in, because there's no telling what with this computer is no telling what might happen. All right, so we left off on talking about macro or microscopic properties and how we look at chemistry using macro, micro, and symbolic in the symbolic realm, the macro realm, and the micro realm. So let's just recap that, and then we're gonna move on to the next topic. All right. So when we said that something was studied in the macro realm, what did that mean?
That we're able to see it.
Able to see it. You're able to see it. You're able to touch it, and you can study it empirically. You don't need any special instruments or anything like that. Now, all this is going to tie in to like physical properties, physical changes, all of that, because physical properties are macro properties that we can, well, some of them are that we can actually see, and some are not macro, some are micro. And then we said that an example of a macro, we talked about like the clouds and the ice versus the lake. But then on the micro scale, we talked about how the water molecules were arranged in each state of that matter, right? In the liquid, the solid, and the gas state. So micro properties are properties of, they're internal. You can't see them, but you can still study them, but you need special instrumentation, and it's invisible to the naked eye. All right. So an example of a micro property would be a bond between two atoms, right? A bond between two carbons, or a bond between a carbon and an oxygen. You can't see that with the naked eye, but there are instruments that allow you to see on the atomic level, even though you can't see the actual subatomic particles. All right, so today we're going to move on from that and start talking about classifications of matter. So let me add a page. Stuff down. 1 second. All right, so that's what we're going to start today, dealing with classifications of matter. This is the 12th. And after class, if you noticed yesterday or Monday, I actually sent you an announcement that's going to be standard. I'll send you an announcement with a link to the video recording from the class, and I'll tell you whether that I posted the notes, and if there's any other pertinent information, all of that will come in the same announcement after each class. All right. Today, I actually have a quiz for you to take, but you don't have to take it until after class, and you'll have until Thursday to complete it. What's the day? Wednesday? Did I say Thursday? No, not Thursday, Tuesday after the break to complete it. All right. It's a simple quiz, and it's dealing with something that we're going to talk about today. All right. So, and there's also a paper, a publication that ties into that quiz. So if you read that paper, there's a link to it. there's a link to that paper. Sorry, that's the dean texted me. And that paper will guide you through the quiz, to help you through the quiz, but it's really talking about the essence of the quiz is dealing with atoms versus molecules. All right. So we're going to start with phases of matter, classifications of matter. And we're going to talk about, first of all, some basic properties of each state of matter. So can somebody tell me what the 4 phases of matter are? Anybody?
Solid, liquid, gas, and vapors.
Okay, close. You got the first 3. You have a solid, a liquid. Let me put some room because we're going to add something to these. Liquid. Very good. You said gas. The 4th state is what we call plasma.
There we go.
All right. Do y'all remember? Y'all probably don't remember this, but you may. In the early 2000s, when plasma TVs became the rage, right? So plasma is, often used. There are plasma torches that can cut through really hard metals, plasma televisions. And so it's actually considered the 4th state of matter, even though it's not really talked about. Most of the time we talk about solids, liquids, and gases. And again, somebody help me define what matter is. What's the definition? Anybody?
Anything that occupies space and has mass.
Good. Occupies space. Let me get my two walking together. Anything that occupies space and has mass, no matter how small it is or how large it is, right? So for solids, solids have a definite shape. And they are rigid. We know that. What else can we say about solids after talking about what we talked about the other day with the macro and micro stuff? What do we know about the molecular arrangement in a solid?
It's more structured.
It's more struck. Very good. Who was that?
That was me.
Thank you.
You're welcome.
That was me. I still don't know who me is.
Oh, Amaya Kaufman-Taylor.
All right. So they have a really defined molecular arrangement. Well-defined molecular arrangement. I'm gonna say atomic too, because there are solids there are elements that are solid, and it's just atoms and not molecules. So they have a well-defined either molecular or atomic arrangement, right? And then we think about liquids. Liquids don't have a definite shape, right? They take on the shape of whatever container you put them in. Right? They take on the shape of whatever container you put them in, and they have a fluid arrangement. Of atoms or molecules. One of the atomic elements, Mercury. Mercury is a good example of an element that exists as a liquid. If you've ever seen mercury spill from a thermometer, it is a liquid at room temperature. It beads up. It's very difficult to contain. It's also poisonous. So liquids don't have that same molecular or elemental arrangement. It's a lot more fluid. And whatever container you put a liquid in, that's the shape that's going to assume. All right, what about a gas? Tell me something about a gas that you know.
I know their molecules are more spacious.
More space, so much more, how do I say that? I'm just gonna say a large interatomic or intermolecular distance. Good, right? Large interatomic or intermolecular distances between the molecules, and also pressure dependent. Right, the volume is pressure dependent, and it takes on both the shape and the volume of a container, whatever container it's in. So I get a semicolon in here. Right, so plasma is different from, it's a gas, but the gas actually has a charge. So it's not just a gas, it's a gas that's made up of charged particles, or what we call ions. Right, so sometimes you'll hear plasma also referred to as an ionized gas. Can somebody, gaze, come on, Russell. Can somebody tell me, anybody, what an ion is? Does anybody know the definition of an ion? This is a great place to just sneak you some good information for later. So an ion is an atom or a molecule with a plus or a negative charge. Right? It's an atom or molecule that has a positive or negative charge. A positively charged ion, we call it a cation. And if it's negatively charged, we call it an anion. Right? That's a really important concept, because when we start talking about molecules and start talking about molecular formulas of certain, when certain elements get together, then it's going to be really important to understand what an ion is, what the charges are, so on and so forth. Go ahead, Saxton.
Okay, so I understand the concept, but there was like a word and it was popping in my head, but then I forgot. What's the word for that? Is it iodized? When it becomes an atom with a
When it becomes charged,
yes,
it's
that word.
ionized. It's right here. Ionized.
Okay.
That's a good question. That's a great question. I knew somebody was gonna. Hold up. There's somebody trying to log in, but they said the link isn't working. They need a passcode. Hold up. Two, 6, 7, 2, 9.
Dr. Russell, can you zoom out a little bit so I can see the
Oh, absolutely. Absolutely.
Thank you.
All right, so again, matter it can exist in different states or phases. It can be a solid, it can be liquid, it can be gas, or it can be plasma. All right. I'm dating myself, but it's all good. I'm 46. I still have a plasma TV. I remember When I bought that TV, it was $3,500. And it's a 50-inch, if I'm not mistaken. And it weighs like 100 pounds. Now you can get a 75 or 80-inch TV for $500 and it weighs nothing because they moved away from plasma to liquid crystal displays or LED displays, right? So that's with technology. Sometimes you want what's hot and new, but a lot of times it's best to wait because tech always goes through the same cycle. It starts when something is hot and nobody has it, they charge you an arm and a leg. When people start innovating and developing new ways to give you the same tech, the prices always go down. So this old man, sharing some wisdom. Because I know for a fact I should have waited and bought that TV, but I had to have it because you know how we do. All right, let's move on to the next topic. And one of the things about matter, sometimes it can look like matter is existing in more than one state. And I think the book gave an example of like sand because it's granular. You can pour it like a liquid, but it's still a solid. But that's really kind of just a side note. That's not in it really important. Now we want to talk about the properties of matter, and then we're going to talk about how to classify it, whether it's a pure substance or it's a mixture. All right, so properties of matter, let's talk about that. And I know this is, it doesn't seem like chemistry. Oh, come on, bro. Hold up. I have to stop sharing for 1 second because student could not get in. A42. Staying there. And I sent the link out ahead of time and everything. All right, sorry about that. That's like stopping class to open the door after you lock it. That is good though. All right, so let's talk about properties of matter, right? And we talked about the fact that matter has mass and it takes up space, right? So the mass of a material, whatever it may be, is a measure of the amount of matter that's there. So whatever, it could be a penny, it could be an electron, it could be whatever. There's a difference in mass, which is a measure of the amount of matter. Right, it's a measure of the amount of matter in an object. And then the weight, which is different, right? Weight takes gravity into account, right? So weight is, and again, a lot of definitions in this first chapter, all just laying the groundwork for when we move forward. When you understand the concepts of mixtures and substances and matter and the different phases of matter and the volume and all that stuff, you start to understand that, then when we start doing the actual chemistry, you can kind of visualize what's happening between those atoms when they're interacting with one another. All right, so all of this is, there's a method to it. It's not just me just boring you to death with definitions. All right, so the weight takes into account the gravity. So weight is the force that gravity exerts on an object. All right. Can somebody tell me this? Let's answer this question. Does the weight of an object change under different gravitational forces? Or let me ask it a better question. Would you weigh the same on the moon that you weighed on the earth?
No.
No. Your weight is based on the effect of gravity, right? The moon is one, I think the gravitational pull of the moon is like 1/6 that of the earth. So your weight would decrease by 1/6, but your mass wouldn't change, right? Mass is not dependent upon force, so it's not dependent upon gravity, but your weight can fluctuate depending on where you are, what the force of gravity is where you are, all right? So let's think about, let's keep pushing this, and let's think about, I gotta move this again, sorry. We're gonna get to that in a minute. Let's think about, again, we talked about this the other day, about the law of conservation of matter. All right. And what does that mean? All right. So let's define what conservation of matter actually means. And I think I mentioned it in class on Monday, but we can talk about it again. You've heard, if you took physics or chemistry in high school, you probably heard a version of this definition. And that is that matter can neither be created nor destroyed. What that really means is, as matter changes from type to type or from phase to phase, the mass remains constant. That's all that means. So when we say conservation of matter, what we mean is, as matter changes from type, because a chemical reaction is actually taking matter and changing it from one type of thing to another. Type to type or phase to phase, the mass remains constant. All right. That's how we can say or state the law of conservation of matter. And one of the examples that the book gave is the actual brewing of beer, right? So the initial ingredients of water and yeast and hops and grains and malt and sugar that you mix together, and heat it, gives you alcohol. It gives you carbonation, as some of the compounds that you start breaking down and releasing carbon dioxide. Gives you different flavors that get released from the hops and from the yeast. And you get all these other things in the beer that you didn't start with. But if you compare the mass of what you started with and what you end with, it should be identical, right? So that's a way to think about the law of conservation of matter, right? As matter changes from type to type or from phase to phase, the mass of that matter should stay the same. Now, the thing about the law of conservation of matter is this. Sometimes, let's say if you're boiling ramen, if you're making ramen, right, you might add a cup of water, but if you boil it uncovered, what's going to happen to the water once it starts to evaporate and you don't catch it?
It changes form.
Yeah, it's going to change from state to state or phase to phase, but you're also going to lose some, right? If you boil a pot of ramen uncovered, when that water starts evaporating, it's just going to dissipate into the atmosphere. So you have no way of comparing the masses, right? But that doesn't mean that water got destroyed. It changed phases and it ended up somewhere else where you couldn't measure it, but that doesn't mean that it got destroyed. The mass, if you were able to catch all the water that evaporated and compare it to the mass of what was left, minus the ramen, obviously, because we're just talking about the water, then the mass should be the same. All right, any questions so far?
No,
All right,
sir.
go ahead.
No, I said no, sir.
Okay. All right, hopefully this is not overly boring. We're gonna get to, when we get to the measurement part, it's gonna get more exciting because there'll be some examples that we're gonna work through in class and do some calculations and things like that. But laying the groundwork is, I don't know if you ever have been told this, but your foundation is everything. And this is laying the foundation for everything that we're gonna study from this point going forward. So we gotta build on a solid foundation as opposed to just building on something that's fleeting. And then when we get to harder concepts, we don't know anything. So we gotta go through we gotta sludge through all of this crap so we can get to something more juicy and exciting. All right. So now let's talk about matter classification. Right, and we're basically going to talk about two classifications of matter. Right, we're going to talk about pure substances, and we're going to talk about mixtures. Right, so matter can be classified either as a pure substance, Russell, or a mixture. Right, and there's a way. Let me pull this chart up and go ahead and, because we can simplify it up front, and then we can go back and define what's what. All right. And if you have that ebook, this chart is in that ebook. All right. So here's the question that we asked to determine whether something is a mixture or if it's a pure substance. All right. If the matter has, the question is, does it have constant properties and composition? Right. In other words, if you cut it in half, cut it in quarters, broke it open, you're able to examine the inside. If it has constant properties and composition, then it's a pure substance. If it doesn't, it's a mixture. Right? Is that clear? Is that okay?
Can you repeat that? I'm sorry.
Yeah. So if it has constant properties, you see this part right here, does it have constant properties and composition? All right. If it does, it's a pure substance. If it doesn't, it's a mixture. You see the little arrow saying, yes, it does, then it's a pure substance. And then if it doesn't, it's a mixture. All right. Then if it's a pure substance, can it be broken down? Right. If it can be broken down, yes, it's a compound. We're going to talk about the difference in a compound and an element and all that stuff. If it cannot be broken down, then it's an element. Right. Meaning, and the element is the most basic form of matter. So we can actually say that right here. Right. And even an element, although it can't be broken down, it is composed of atoms, right, which are even more basic, but you can't, but the composition is uniform, and so we still consider it a pure substance. But you can't simplify it chemically. Like you can't take an element and chop an atom in half and get a new element. It doesn't work like that. Right. So that's really the most basic class of matter. And then on the other side, if it's a mixture, it's either going to be homogeneous or heterogeneous. If it's uniform throughout, like if you're drinking a Coca-Cola, that's a mixture of all types of stuff, sugar, the cola flavoring, all of that. But when you drink it, you can't see the different components, right? So that means it's homogeneous. It's everything goes together, right? That means it's uniform throughout. If it's not, then it's heterogeneous. So I have an example here of something that's heterogeneous. How many of you have eaten at Bonefish Grill before? Anybody?
A bonefish grill?
Never had
I
Bonefish?
have.
Okay, one person. It's a restaurant. They specialize in seafood, but they serve everything. If you've eaten there, go ahead.
Oh no, I'm just getting some information. So
Yeah, do you live in Auburn or are you off campus?
I'm on Tuskegee's campus.
If you get a chance, this is what I'm gonna do. The next time I ask a question or whatever, I'm gonna attach some lunch money to it. If you answer it, you can go to East Chase in Montgomery with your mask on and get your food to go. But they have a bonefish in East Chase. Really good restaurant. But they serve,
You said in Montgomery?
yeah, in Montgomery.
Oh, I live in Montgomery.
Oh, well, you good then. Go to East Chase. It's in East Chase. It's over by on the other side of the Books A Million bookstore. But the point is they serve this pesto, olive oil, salt and pepper mixture, but it's heterogeneous. It's not all together like the pesto and the salt and the pepper. You can see it in the olive oil. So that's an example of something that's heterogeneous. We'll talk more about that. But so matter can be either a mixture or pure substance. If the pure substance can be broken down, it's a compound. If it cannot be broken down, it's an element. If it's a mixture and the mixture is uniform all the way through, in other words, it's a complete solution, everything is dissolved up, is homogeneous. If not, it's heterogeneous, right? So let's think about these pure substances, all right? And let's think about an example of a pure substance, because I know it kind of, right? Again, it has a constant composition. Right? And what I mean by that is no matter how much of a pure, especially if a pure substance is made up as a compound, no matter if you take a gram of it or a kilogram, the percentages of whatever that compound is made of is going to be the same. And so one example of that is sucrose. That's table sugar. So let me actually show you what that looks like. Don't panic when you see this because you haven't had organic yet. So you haven't seen 6-membered rings. Right. That's oxygen. That's CH2OH. This is OH. This is what table sugar actually looks like. The white sugar that you put on your cornflakes. I probably don't even eat cornflakes. Now I'm really dating myself today. OH, OH, OH. So this compound, that's what this is, right? Because it's a pure substance and that it has a constant composition, but it's also and what I mean by composition is the atoms that make it up. Right, so when I look at sucrose, which is a compound that's made of both fructose, which is a sugar, and glucose, right? This is an example of a pure substance that is a compound, right? But when I look at that, the composition of it is the percentages are always going to be the same. 42% carbon, 51%. I say 50. I don't need to put the decimals on here. 42.1% carbon. So 42.1. no matter how, I can take a sample as large as the Empire State Building. When I analyze it, it's going to have the same composition, 42% carbon, 51.4% oxygen, and then 6.5% hydrogen. Right, that's what that means when you say something has a constant composition. You can cut a gram of it, you can cut a kilogram of it, you can cut a ton of it. When you analyze it, the atomic composition is going to be the same. All right, that's what that means when a pure substance is a compound and has a constant composition. Does that make sense?
Yeah, it does.
All right, so if I take that sucrose and I heat it up and it undergoes a physical change or chemical change, I'm sorry, you can break it apart, you can break it down. That's what that means. Also, if a pure substance can be broken down, then we call it a compound. If it cannot be broken down, then we call it an element. So this is an example of a compound. Let me take this out of the way. An example of an element would be just like sodium. Right? Sodium cannot be broken down any further than it already is. So this is an example of an element, and it's a pure substance. And when you, again, pure substances can be either compounds or elements. Compounds have multiple atoms, different arrangements, and if you react them chemically, you can convert them into other stuff, right? Just like this sugar, sucrose, I can break this bond right here. We haven't talked about bond breaking. That's when you get to organic, but this is a bond between oxygen and carbon. I can break that bond. Once I do that, I've altered that compound and made it into something else. All right. So let's think about this in terms of properties, right? Because for pure substances, if you combine elements, to make compounds. All right, so if you combine elements, you make compounds, right? And even when you combine elements, you should expect some change in the chemical and physical properties of the compound, right? So compounds will have different chemical and physical properties from elements. And let me spell that out. So you're gonna have different chemical and physical properties when you compare the compounds that you create from elements to the element itself. Let me give you an example. If you take sodium, right? And if you've ever seen, how many of you have ever seen sodium? Anybody? Like in its elemental form? Sodium is low key, highly explosive. And you have to store it in like mineral oil. If you sit a block of sodium on the bench top, eventually it's going to explode because it will absorb moisture from the air. It's highly explosive when you expose it to water. So you have to store sodium in mineral oil, and it's very soft. It's a very soft metal, easy to cut, but you have to store it, excuse me, in mineral oil to keep the moisture off of it. So you take sodium, which is a solid, a silvery solid. And if you take chlorine, I'm going to do my best to show this as a gas, my little crappy cartoon gas It's a green gas, greenish yellow gas. Taking those two apart, they're both elements, right? They're not, this is not a compound. These are two separate elements. But if I put them together, and let me just say this, if I put them together, I get a compound. Right, so elements combine to give us compounds, and the compounds can be broken down. All right, if I take those two and put them together, I get table salt. I'm sure many of you already know this. If you eat a spoonful of sodium, you will die. If you inhale enough chlorine gas, you will die. But when you put those two things together to make the compound sodium chloride, right, you can put this, you can eat this. Not if you eat too much of it, you're gonna end up with hypertension and you still might die. But hopefully, you monitor your salt intake. But you can put those two things together and boom, you can eat that. But you can't eat either one of the elements or consume either one of the elements separately because they're both poisonous. All right. All right, any questions? Any questions about anything so far? All right, let's do a quick discussion about mixtures, and then we're going to move on. Let me see. I think I'm going to hold off on talking about measurements until Friday. So Thursday, when we meet, we're going to work through some examples dealing with the first part of what we've discussed. So what matter is, the types of matter, phases of matter, compounds, mixtures, macro, micro. We're going to have a discussion about that on Thursday. All right, so let's talk about mixtures for 1 second, and then we'll be done. We actually got about 2 minutes left. Right, again, a mixture can be homogeneous or it can be heterogeneous. Right, so something is a homogeneous mixture. Well, first of all, what is a mixture? A mixture is something that's composed of two or more types of matter, right? So you have let me just say a combination of two or more types of matter.
At the top, does that say table salt?
Yes. Underneath the sodium chloride?
Yes.
Yes. Let me
Thank
fix my B. I'm sorry. I tell this to all my students. When I was in elementary school, they used to give us grades for handwriting. I always got bad grades for handwriting. So that actually kept me off the honor roll 1 year because I got a C in handwriting. But then my mom came and raised sand. That's a long story though, one of many. All right. So a combination of two or more types of matter. And this is a physical combination, by the way. You can when you compare what a mixture is to a compound is really a chemical combination, right? Where atoms are coming together and bonding together, whereas a mixture is a physical combination. So if it's a physical combination, that means it can also be separated physically. So if you put it together physically, you can separate it physically. It's almost like if you took a bucket of iron filings and dropped it into a bucket of sand and mixed it together. If you took a magnet, you can run it across that and pull those iron filings back out. So that's what when we think about a mixture, it's a physical combination of two or more types of matter, right? If it's homogeneous, right, that means that it is uniform in its composition, meaning if I take a bottle of Gatorade and I take a teaspoon of it, and then I also take a cup of it and I compare what's mixed into it, then it's going to be the same composition no matter what. So homogeneous mixtures have the same composition. And then heterogeneous mixtures they have varying compositions depending on what you take out. Right, a good example of this would be Italian dressing. If you eat that, right, you can take out a spoonful of Italian dressing, and you might have 3 red peppers in that spoonful. You take another spoonful out, you might have 1 piece of red pepper and 10 pieces of garlic, right? So a heterogeneous mixture it varies in composition, right, from point to point. What else do I want to say here? Oh, so the way that you can tell a mixture from a compound is, again, the way you can separate it. If you can physically separate the components, it's a mixture. If you can't physically separate those components, then it's a compound, right? Compounds normally have to be broken down chemically, whereas mixtures can be broken down physically. That's another way to say that. So let me write that in here, and that'll be the last thing we mentioned. All right, so compounds are chemically separated. And mixtures are physically separated. All right. Any questions about anything? Hopefully, we're all on the same boat and being engaged and attentive, because I promise you, this semester is going to go by so fast, and you're going to look up and it's going to be April. So you got to stay engaged so that you can get everything that you're paying for. Go ahead, Saxton.
So because you used water and sand as an example, would you say salt water is a homogeneous or heterogeneous mixture?
Salt water is going to be homogeneous.
Mm-hmm.
Yeah, because salt water is it will become a solution, right? When you take the salt and dissolve it up in water, if you can't see the salt physically, then it's going to be, that means it's homogeneous. It's the same composition.
Right.
Mm-hmm.
Okay.
Great question. Great question, and great example too. All right, other questions? All right, I don't know about how y'all feel about this, but this is exciting to me. Teaching G-Chem, this is fun. Yeah, who put that in here? Okay, yeah, but homogeneous mixtures, yes, are solutions. If it's a liquid being mixed with either another liquid or a solid, then yes, we call it a solution. All right. Any questions about anything? All right. And the reason I say that, Saxton, is because air is also considered a homogeneous mixture, but it's not a solution.
That was what I was thinking. It's just when you said sand and water, and you said if you take a magnet and pull it out or whatever, but I was like, really, you can evaporate the water and still, separate the water and the salt. So I was like,
absolutely, you can. But again, that's a physical operation. Is that right?
Right.
So heat it up, drive off the water, and leave behind the salt. That's a physical operation. And people actually do that. Like if you, if you're stranded at sea, you can't drink salt water because it'll make you really sick. But you can distill off the water and leave the salt behind and drink the water that you distill off. So, but it's again a physical way of separating those two things. That's good though. Good thinking. I like that. All right, we got to stop here. We're 5 minutes over time. So hopefully if you have any questions, just email me And what I'll do, I'll post the notes and I'll post a video